physical sciences student, therefore I'm not expecting you to have previous knowledge of Python. I'm hoping that you're previously exposed to logic though, so hopefully this won't go too aggressive. So this presentation will be split into two parts. The first part, I'll be covering basics of Python syntax itself, since I believe that trying to teach the libraries without teaching the syntax is only going to confuse you. And then the second half, we will actually be showing, I'll be making a demonstration showing how to actually do data science using Python, using some of the SciPy libraries. More on some of those terms later. So yeah. To start with, Python actually has two versions, and I actually don't have a slide for this. I didn't get it written in time, but there are two major versions of Python you have to be aware of. There is Python 2 and there is Python 3. In modern times, always use Python 3. Python 2 is end of life, should not be used, and I'm simply acknowledging it here so you guys are aware that it still exists. If you do find yourself in a situation where you need to write Python 2, my commiserations, talk to me after the lecture and I'll show you some tricks to make it more Python 3 compatible. So anyways, with Python itself, the first thing we should do is I'm just going to open a terminal. At this point, I trust everyone here is familiar with the terminal, right? Let's see, I should be able to make that bigger. So if you have Python installed, note that if you have Python, that's actually going to refer to Python 2 if it's installed on your system, unless you're on Red Hat Linux. So don't use that. Instead, you have to use Python 3, which will get you into a Python 3 interpreter. In this case, my machine has Python 3.8.10 installed, which is fine. That is the current version of Python 3. So what we're given here, this is the Python REPL. A REPL is it reads your input, it evaluates it, it prints the result, and then it loops. That's all it does. Because Python is an interpreted language, we don't actually need to compile our code prior to running it. Meaning, I could just put some code in here, and I'll explain what this does in just a moment. If I can type it correctly. All right. So I will go into more what these things mean. For the time being, I'm just going to wave my hand and say that prints is something called a function, which takes your argument and puts on standard output. I'll go more into functions in a later slide. And then this in the middle, between two double quotes, is what's known as a string literal. More on that in just a minute. So what we've demonstrated here is just basic syntax. Now, if you're trying with a programming language, this is probably the first thing you're going to want to do. In C++, you'd also do something completely different. You would do something like include IOStream int main with whatever arguments, and you do standard cout and then you would hand that off to a compiler, right? That is roughly equivalent C++ code for the Python that I just demonstrated in a single line. So that demonstrates one of the first values of Python. Its syntax is incredibly simple, but it's also incredibly powerful. By the way, if anyone has any questions, feel free to interrupt. The next thing I'm going to be covering is, let's see here, comments and string literals, apparently. So going back to Python 3, if I were to write anything that starts with a pound symbol will be ignored. So if I were to do the exact same line we had above, right? Nothing will happen because that line was actually ignored by the interpreter. You can also do it in the middle of a line. So if I put something like this, just to demonstrate that we have invalid syntax, right? It doesn't know what I'm talking about. And put a pound symbol, you'll see that it prints hello, but ignores the invalid stuff off the end of it. That is, comments are there for documentation. It's for you to express to whoever's reading your code what you were thinking when you wrote that piece of code. That someone may be you, I don't know, maybe the next day or months down the line. And you'll also find that this is all over my example code base. The examples that go with these slides are, have comments all over them explaining what the code does. So that is the comment. You also have things like string literals. There are actually three ways to make a string literal. This is the same thing as this, which is the same thing as this. I'll go more into what the equals means in the next slide, but the three of them are the same. The only difference is which character is escaped. So if I were to try doing hello, and I want to have that in the middle of that, it's going to tell me that's invalid syntax. But if I replace the outside of that, oops, and get the double quote in place, you'll see that the single quotation mark was put into the string. That is the only difference between the three string forms. Well, only noteworthy difference. That's string literals. The next thing we're going to cover is basic math operations. Say 4 plus 3. 4 minus 3. Now with division, what do you think this will output? Will someone like to venture a guess on what this will output?
1.
You would think that, but you'd be wrong.
Just 1. Oh.
In Python 3, the default division symbol, which is just the single division / with that backslash, either way, does floating point division. More floating points in the next slide. You also have, if you really want integer division, you add a second division marker, and that will give you the 1. So you have both forms of division. You have both integer and floating point division. By default, you will do floating point division, even if what you're dividing are integers. Let's see here. You also have integer division. You also have exponentiation. So if I want to say raise 2 to the 32nd power, or okay, let's do something smaller. Say 2 to the 4th power, right? The 2 stars here indicate that I'm raising the left-hand side to the value on the right-hand side. Make sense? We also have modulus if you want that as well. So say how many, if I were to divide 42 by 3, oh, that actually divides cleanly. Okay, that was a really interesting example. Okay, let's try doing 43 by 3 then. You'll see it has a remainder of 1. So 42 is divided by 3 cleanly, exactly 14 times. 43, however, will leave a remainder of 1, the 0.3 repeating. So if you take the modulus, that will give you the result of integer division, which can also be useful. So those are the basic math operators. Now that we have math, the next thing that we are going to talk about are variables. So now that we say have the result of this operation, right? We can assign this to a name because, doing math, without being able to do anything with the result of that math is not very useful. So what we can do is we say x equals. This x here can be any valid Python identifier, which basically means it must start with a letter. It cannot contain spaces and it cannot contain special characters. Those are the only real restrictions. Otherwise, you're allowed to do almost anything. It would also not be a identifier. For instance, I cannot say async equals. It's going to tell me I'm not allowed to do that because async is actually a keyword. More on that in a bit. So now that we have variables, let's say do area. So we have length equals 42 and say the height is equal to 17, right? And say we wanted to say this is a rectangle. Area is equal to length times height, right? If I spelled my own variables correctly. All right. If we now print area, we'll see we get 714. If we did 42 by 17, we'll get the same number because it's the same operation. With variables, you can use them in the same places that you can use literals. So the 42 and 17 here are what we call literals. They're just this value. They're literally this value. You can assign them to names, and then you can use those names in expressions. Print is also a name, funnily enough, and you can actually assign to it. I don't recommend doing so. For instance, if I do print equals 147 or 127, and then try calling it, well, it's not going to work because this is now the wrong type. And I'm just going to go ahead and reset my interpreter. What I'm demonstrating there is the Python interpreter does not get in your way. If you want to do something, Python will let you do it, even if it's not necessarily the correct thing to do. Modern tooling will prevent you from doing some of this. For instance, I believe if I were to go into just a random Python file, don't worry about what's in here, I'll come back to that. If I try doing print equals 12, it should actually give me a warning here, right? If I could press the right keys. Yeah, it's warning me that I am shadowing a built-in name. A built-in is something that the interpreter gives you for free. For instance, the print function is something that you are given for free. You don't have to do anything to use it. And my ID is warning me that I am shadowing that name, which is exactly what we did. All right. Let's see. You can also do basic introspection. Say you have a variable that you don't know what is. This is a string literal. Say we know we have X. We don't know what type it is. We can just pass it to the type built in, and it'll tell us this is of a class string. So this is just basic introspection that allows you to have a look at an object and it'll tell you what it is. All right. Boolean operations. So I hinted at this in a previous slide. Boolean operations are what allows us to do things like Boolean algebra. Is X equal to Y? So similar how we can do an assignment operator here, the single equals is an assignment operator. But if we did X double equals Y, we're now doing comparison. In this case, 12 is equal to 12, and therefore the result is true. If you want to do not equals, you can also do that. And if you want to do relational operators, such as is X greater than Y, well, that's not true, but it is greater than or equal to Y. You also have less than and less than or equal to. There's also another thing you can do with this. You could also do not. So you have two types here, two values here that are also built-ins, true and false, which are your Boolean types. You can also negate them. The not operator negates a Boolean. That's all it does. So if I were to say X is equal to Y, and I say not X equals Y, while that is technically a true statement, this is actually bad style. You really should be using not equals instead of using the not in this particular context. Well, more on the indentation error in a minute. So that's Boolean operators. Types. There are a bunch of types. So similar to how you have different types of fruit, like you have an apple and an orange, or you have different types of cars, like a Tesla or, I don't know, a town car. Different types can do different things, and they have different data. So there are various types that can be used. Now, this table is just a couple noteworthy ones. You have string, bytes, floating point. I left a link in the slides linking to an educational resource. You can learn more about floats. You also have none and a couple other things. With types, I'm actually now going to switch to my IDE, and I'm going to create a new file, and I'm just going to demonstrate a couple things here. Let's see here, or which file did I use for this example? Or I may not have used an example at all. Okay. New Python file. So with types, I said there are things you can do with them. For instance, the type of a fire alarm supports a method called pull. When you pull the fire alarm, it does something. Similarly, if we have a string, right? And we know that the type of data is string because we know that because it's a string literal. Well, what can we do with the string? The dot operator allows you to access the attributes of an object. In this case, my ID is telling me that it knows it's a string, and these are all the different methods that you can do on a string. The list is actually kind of long, and I'm not going to go over all of them, especially the ones that have special names. But there's one that we're going to use here called split. And split returns a list of words in string using sep as a delineator. And I'm just going to do words equal, and then I'm going to print the words. And if I run this, you'll see that we get a completely different type. This is a Python list, and I'll be going over that, I believe, in my next slide. For the time being, you'll see that we no longer have a string, we have a collection of strings. So this is just demonstrating that built-in types have functions. So do the types of things like a data frame, which I'll be going over in the second half of this presentation. And that stuff isn't really relevant. So let's get into the built-in containers. So speaking of list, this is the precursor to the Numpy ND array. More on that later. But for now, a list, say 1, 2, 3. A list is a container. It is a ordered container, meaning the order in which you put items into it is the same order you'll get items out of it. So if I were to do, so I could say X, and you can also address into this, say X of X2 is equal to 42. And if I were then to print X and run this piece of code, you will see that the third element has been overwritten to a value of 32. This is highlighting that in Python, all arrays are 0 indexed. This also shows that you're allowed to do an assignment operation. Of course, you can only use integers when you're working with a list. If I were to put this in here, my ID actually tells me this is wrong. If I can get it to show you the warning and not just the highlight. Okay, I really haven't completely fixed it, but it's telling me that this is wrong. And if I were to try to run this, my ID will be absolutely correct. It's going to tell me, Python here is going to tell me, it's going to raise something called an exception. It's going to say list indexes must be integers or slices, not strings. Well, that's interesting. What are slices? Let me show you slices. So say you have a larger amount of data. I'm just going to add a couple extra elements here, right? Doesn't really matter what values I use, except for that one. Say you want every other element, right? From the 0. You can actually do something called a slice. Say I want to start from the beginning through the end, and I just want every second one. And if I were to run this, you'll see that it cuts out every other element. Similarly, say I only want a certain subset. Say I want the third element through the 6th element, right? And that is a slice. The Numpy will build upon this in the second half of the lecture. But for the time being, that is how you can use a list to store ordered data. Oh, and also you can do other operations, like if I wanted to sort this data, x.sort, and then print, question.
Does it allow aggregation?
Aggregation, I'm not familiar with that term in this context.
If you had another of the same data type, could you make it equal to it and copy the whole thing to it?
So something, if I understand your question right, you're probably referring to this, yeah?
It's like when you're trying to get an array to equal another array.
Oh, so if you want to do a comparison, okay.
Like assigning another array to an empty array, something like that.
No. So say you want to make a copy of the array?
Yeah. So
Yeah, you can do that. That's actually one of the methods on most of the built-in containers is a method called copy. When you copy it, it will create a shallow copy of the data and assign that to a new variable. And if I were to then print y, right? It's equivalent. Note that you cannot do y equals x. I mean, you can, but it won't actually do what you think it does. So say I then call x.clear, right? What do you think the value of y is? Well, it's going to be empty. Spoiler. The reason being is the way that variables work is if you're familiar with compiled languages, this is a shared reference. Names are references to objects. When you do y equals x, you're saying y refers to the same object as x. But That is an implementation detail. If you want to copy an array or another container, you need to do so by copying. Then it will work the way you expected it to. Make sense?
Yeah.
Awesome. You can also, let's see, getting back on topic, if I wanted to sort the array, x dot sort, and then print x, you'll see that the data is now in order. I can also pass it reverse, I believe it is, yep, to get the sort in the opposite order. It will now sort in the opposite order. That's just some of the things you can do with a Python list. You can also do other things like say you want the sum of this array. You can pass the array to sum. And you'll get a number that is, if you added up every single value inside of that list, that's what that would be. You can also get the length of it. Print the length of x. Sum and length are built-in functions. There are 8 elements in this array x, so our length is 8. So yeah, and those return types are integers. Let's see, is there anything else I wanted to specifically cover? Oh yeah, there's also built-in for max. So you want to know what the biggest number in this array was? Let's see, okay. It will tell me that's our biggest number, which makes sense because that is in fact the biggest number in this array. All right. This is not an exhaustive reference. I provided standard library links as well to help out. And for the sake of time, I'm going to move along swiftly to loops. So we have our data now, right? I'm just going to go ahead and copy this out of the example. Or not. There we go. There we go. Okay. So a loop, or specifically a for loop, allows us to do something against every item in the collection. This is the equivalent C++ is a lot more complicated than that. So what we're saying here is for every item inside of data, we're just going to print the item. And if I were to run this right now, you'll see with our data being, it'll print 2 and then it'll loop. It'll see 1, it'll loop. It'll see 4, it'll loop. It'll see 7, so on, so forth. For loops are an extremely powerful construct that can be very useful for processing data. Similarly, there are other types of items that are iterable, is the proper term for it. For instance, the built-in range. I'm using print simply for the sake of demonstration. Normally with code, you're not going to be using that command all that much. So you'll see here, it's going to iterate a bunch of times. The range is a built-in that you give it a start, a stop, and you can even give it a step. So you can tell it to give you every third number, right? And what it returns is an iterable, which is why we're allowed to for loop over it. We can also say cast it to a list. And that's the wrong one. Okay, and you'll see that it's cast to a list. So that's for loops. Next thing we're going to cover is functions. I am skipping around slightly to remain so I have enough time to actually get to the meat of the subject. So a function is a reusable piece of code. Say you want to, I don't know, you're doing some science and you want to represent the path of the altitude of a rocket given a function. Def y of t is equal to, say, t squared plus 4, right? You could do something to the effect of, say, 1 times 2 plus 4, 2 times to the power of 2 plus 4, 3 times 2 plus 4, so on and so forth. But that's going to get tedious really, really quickly. And this is just a very simple example of how this is extremely tedious. Just get rid of my ID warnings. Functions are an abstraction. They can say, well, something else has the code I want to use. And that code is reusable. All I have to do is give some values. So if I do say def y of t, this is the syntax for y. This is the minimum syntax. Def is a keyword that says I am defining a function. You give that function a name. In this case, I'm going to call it y. And inside of these parentheses, you can have 0 or more parameters. For instance, if I did that, this is perfectly valid. This would actually run and not produce any problems whatsoever. But it's not going to be terribly useful. Also, because I had this question before. These three dots, this is known as an ellipsis. This is in this context, it's equivalent to pass. It's a no-op. I'm simply using it to satisfy the syntax. Another thing you will notice here is that there are no brackets. Instead, I have white space. Python has significant white space. So if I were to do this and just get rid of that white space, it's actually going to tell me this is invalid syntax. And if I were to try to run this, it would also tell me it expected an indented block. I should have called this out when I was telling you about the for loops, but I slipped my mind. So every control structure in Python uses indentation to signify what its scope is. So for instance, if I re-indented this, this is in scope. This is also in the scope. This is not in the scope of def y. But more clearly, def y of t print in function. And if I were to run this, you'll see that only one of these print statements runs. The print statement that is not indented, or more specifically, it's actually the unindent. Only the out of function will print until I call y. If I were to then call y 42, and I'm not going to give you the return value because there isn't one right now, you'll see that the rest of the code runs. And I can do that more than once if I really wanted to. A function is simply a piece of reusable code. So say we go back to saying return, and I'll give you the return allows you to give a value back to whoever called you. Say t to the square plus 4, right? We can now say that our x is equal to t0, t1, t2. Or I guess that's actually y's, aren't they? Yeah. All right. And if I were then to print x, you will see that we have numbers because our function returned some numbers. We'll be returning to this example when we get to Numpy in a short while, because this actually goes even further once you get to those libraries. So, any questions on functions before I continue? Okay. Next thing that I'm going to cover are modules. This one's more or less a definition slide. Your Python source code is written into .py files. Every .py file is what's known as a module. Every module has a namespace, and all modules exist within the project's hierarchy. Modules may exist simply at the top level, or they may exist within packages. Well, what's a package? Well, that's also a simple definition too. A package is simply a folder in your file system that contains one or more Python files. In older versions of Python, you're actually required to have a dunder init.py even if it was empty. In newer versions, that's not strictly required, but it's good practice to keep one in there anyways. Libraries are packages. Libraries are packages containing modules that do a certain thing. So, for example, we're now going to talk about imports. There is actually a couple Easter eggs inside the Python interpreter, one of which is import this. Yes, this is actually valid syntax, and it will give you the Zen of Python by Tim Peters. While it's not necessarily adhered to these days, I find this is invaluable advice to give any beginner Python programmer. The most important thing is simplicity. Simple is better than complex, and complex is better than complicated. Specifically, simple is better than complex. In Python, what you want to do is generally going to be simple. Now, whether simple means is behind a bunch of function calls in a library that you don't know what's doing, that's fine. That's called abstraction. Or, I don't know, just adding two numbers together. Both of those are simple. But simple is better than complex because simple is easy to understand. Oh, namespaces are a great idea. Let's do more of those. Modules have namespaces. So now that I've shown that, I will show how you can actually use the import system. So the example code for this project, as well as the slides itself, are up on GitHub. And I have the example code. Like say this demo types that I've been typing in here, right? If I were to go into a Python interpreter at the root of this project, which I'll actually do this, I'm going to use one of my built-in tools. And I were to do from UCI Bootcamp 2021.examples.demo types import y, which executed some code because, okay, I'll explain what happened here. So import allows you to say, ask the Python interpreter, go find this module or package and bring it into my scope. The from is used to say, I only want to get one or two names out of this. Yeah, okay, good, it is showing. So what happens when you import a module for the first time is the module's top level code will execute, which is why we actually see this output, because we've loaded def of y, then we see the x, and then we printed x. That occurs at the module level. If I imported this again, just for demonstrational purposes, you'll see that nothing happens because imports are idempotent, meaning they only occur once per every time you've launched the Python interpreter. No matter how many times you've imported a module, it will only execute the module's top level code once. So what can we do with imports? Well, if I call y of 42, or say y of 7, it's as if the function y, which is actually defined somewhere completely different, is in my current scope. This is how we use libraries, which I believe is going to be the next thing. Yep. So there are a bunch of standard library components which can make writing general Python a lot easier. For instance, pathlib is one of the ones I always love bringing up. It solves one very interesting problem. If you're working on Windows, your paths will look something like, and I'm just going to open up my editor so you can see this. And I'm going to make this nice and big. If you're working with Windows, for instance, your paths are going to look something like C, I believe it's uppercase, users, user, desktop, right? That is a Windows file path. You can tell because of the C colon. In a Linux-based file system, you don't have file letters. You instead have things like mount points. The roughly equivalent path would be home, user, desktop, right? But actually, there's actually a difference here. I believe, let's see, PWD is going to try to throw away around. It's actually the other way around. Windows doesn't really care too much, but it's actually the other way around. That is a Windows path. You'll notice that Windows tends to use forward slashes. It will understand backslashes too, but Linux is not the same. If you try using the other type of slash on a Linux path, it won't work. So that translates to, well, I want to open a file that's on my desktop in Python. How in the world can I do that when file paths are so inconsistent across operating systems? I'm not going to give this to my friend who's running on Windows when I wrote this code on Linux. Well, that's what pathlib solves. So pathlib abstracts the file system layer. It makes it so you don't have to care what kind of file system you work on. You don't have to care if there's anything special in the path like a symlink. Pathlib doesn't care. So to demonstrate this, I actually have an example. I believe it's the pathlib example, which I actually showed yesterday, but I'll actually go into more details now. Import pathlib brings that library into scope. This library is built into Python, which means you don't have to install it. I can say that, well, say I want to get access to something that's in my current working directory. Well, I can just instantiate a path with no arguments. I can then divide it using the division operator below. I'll make this bigger for you. To get into the data subdirectory. And then I can divide it again to get access to a specific file. If we actually look in the file browser, if you run this from the root of the project, it'll open up the data folder and it will grab 0502. It'll open up this CSV, which we will be using to demonstrate how to do data science in soon. But anyway, so if we were to run this piece of code, Pathlib example, if I were to just type this into my terminal, and I'll just to demonstrate it, assuming this is in the correct directory, we'll find out in a moment here, import Pathlib. I'm just going to actually copy that piece of code. That's the whole point of making this code available to you. Let's see. Okay, so a path object has multiple methods on it. One of them is a method called exists, which simply tells you, does this object actually exist on the file system? Because I can give it a completely arbitrary path here. This does not exist on the file system. And if I say target exists, it's going to tell me this obviously does not exist. There are other methods you can use. One of them, I'm just going to go back to the correct target definition, is called read text, which will give you the text of the file, which is something that's incredibly useful. So, and you can then just do something like this. I'm just going to go ahead and copy this entire fragment of code into here and call it. And you'll see it dumps out as a list of lists. That's really hard to see, actually. The cells within our CSV. This isn't simple now, is it? This isn't actually very easily usable to do data science. So the next thing I'm going to tell you about is how to actually do that, but better. The next thing we're going to be talking about are libraries. Python has the benefit of having great library support, meaning if you need to do something, someone has probably already written and published a library. If you need to read from a serial device, such as a scientific instrument, PySerial has you covered. Want to do machine learning? You can pick between TensorFlow and PyTorch. Those are the two common libraries for that. If you want to do a web server written in Python, your two popular options are Flask and Django. Other libraries do exist as well, but those are the two major ones. And of specific relevance to us, we're doing data science, right? Well, the SciPy, or the scientific Python community, has you covered. Oh, and if you want to do stuff with quaternions because you're doing physics homework, well, there's also a library for that. There's a library for everything. I could go on, but we could be here all day listing all the libraries and not actually show anything that would be greatly useful. Third-party libraries have to be installed. That goes into dependency management, which if you have time for at the end, I will show you. Both Anaconda and CPython have different tools for doing this. Anaconda being a Python distribution that's third-party, that's specific to data science or doing scientific Python, but PSA is CPython, which is the default Python distribution, will do everything you need anyways. Bless you.
Thank you.
Anyways, so the first of the third-party libraries I'm going to be talking about is Ipython. So I've shown you now the standard Python REPL, right? The standard Python REPL has some shortcomings. For instance, if I did something like this and realized, oh, well, I made a typo on the previous line, I can't go back to it. I can't edit it, not that I've given it over to the interpreter, right? Well, that's not necessarily the case. So I'm going to show you Ipython, which will also come up in the next any slide on Jupyter Notebooks. Python 3, I believe is the command. So Ipython is another interactive REPL. It does the same thing as the standard Python REPL, but better. It's also used in data science. When you open up the REPL, and I actually closed over that really quickly, I'll show you the full thing. It'll tell you your Python version, and it'll tell you which version of Ipython you've got. It'll also offer some help. More importantly, you have in, which represents an input line of code. By default, this will start at 1 because in0 is actually used to print this, and you don't need to worry about that. If I do a simple map operation, it will actually tell me what the output is. Out1 is equal to 7. And say I am somewhere really far down, but I know that in1 contained a calculation I actually wanted to get back. Well, out is a variable, meaning you can access it. It's a list. You can access it. You can also access in one if you really, really wanted to, which will give you which will give you the string version of the input that you gave. Going back to the example I gave earlier, well, that's not a valid English word, but I can use my arrow keys to go and rewrite it because I haven't actually given it over to the runtime yet. All right, so Ipython is like the Python REPL, but it's better. I recommend using it over the standard REPL when you have the option. That's Ipython. Next one I'm going to talk about is Numpy. Numpy in the ND array. So now we're actually getting into the domain-specific stuff. Numpy is at the core of most of the scientific Python libraries. It provides efficient storage for numerical data. I'm going to go ahead and let's see, I can't do it from there, so we'll do it from here. All right, so if I go back into my Python console, import numpy as np. This is another syntax. The as allows you to rename and import. If you look at any of the standard documentation for numpy, it's always going to use this form. I don't know why they do that, but that's the choice that they've made. And for the sake of not confusing you guys when you go and read documentation, I will also use this form. So what can we do with numpy? Well, let's create an array, right? And do some compare and contrast with the built-in array types. So I'm just going to copy some data out of my examples. Oh, actually, okay. Let's see here. Why? Oh, no, I didn't. From secrets, import brand below. Yeah. Okay. So now we have two lists. Well, one's a list, one's an array. What I've done here is I've generated a vanilla list just by using some random bytes below 232. And I just generated 500 of them. This is for further reading, the search term here is going to be a list comprehension. And then I simply converted that into a numpy array by calling np.array and passing the list. You can also generate numpy arrays directly, and I will show that in a little bit. So if we look at vanilla list real quick, that's a mess, but so I believe will be the array. It's just a slightly different rendered mess. If we look at this more using tooling, that doesn't actually really help too much. Okay, whatever. So remember how we could say we could call sum on the vanilla array? We can also call that, I think we can also call that on the Python array, right? We can, but we can also call array.sum, which will actually be faster, especially for large sample sizes. Another thing we can do, which we cannot do with the vanilla Python list, is something called broadcasting. So say we have a 1, 2, 3, right? I can't just add 4 to that because that's a concatenation, and you can only concatenate 2 lists together. However, if we say our array, let's see, numpy.array 1, 2, 3. Sorry, it's np in this context. We can do it here. This is using something called broadcasting. Basically, what happens is if you try adding a scalar to a numpy data type, it's actually going to expand that scalar into an array of the same dimension and then do a element-wise add to it, which is actually something incredibly powerful. Remember back in demo types where we have this function here, this def y of t? Well, if I were to import that from UCI Bootcamp 2021 examples, demo types, import y, and I pass, instead of, we can call y with 4, right? Well, what if I pass y with x? Well, it still works. We get the same calculation, but in a more efficient manner. One of the things that Numpy does is it makes doing numerical computations incredibly efficient. The equivalent Python is slower. This is not necessarily noticeable if you only have three values, but if you say have thousands of data points and you want to do the same operation on, Numpy will be a lot faster. You can also do other operations. Like, I actually raised to an exponent before adding. You can do any basic math thing to it. You can even do basic vector stuff with this. So that's nice. There's other things you can also do with it, but let's now talk about the Jupyter Notebook, which is another thing that I have installed. I will show you the form that is not in Jupyter Notebook. I'll show you the form that's not integrated into my IDE. So inside of this, we get a file browser. This only exists on your local host unless you specifically tell it to serve to the network, which lets you look at all the files that you have in your thing. For instance, data. Well, what's inside data? Well, we have some CSVs. Again, this is not very readable in this form. This is intended for a machine to consume, and we have a machine to consume it with. But when you're doing data science, your odds are you're going to be working inside of a Jupyter Notebook for reasons that I will show as I start processing this data, which I believe is going to be the very next thing I am going to do. Yes, I am, because I don't know I have a whole lot of time left, do I? Okay, so let's actually show you how to load this data into the Jupyter Notebook. Up a directory, and I am going to have that open side by side, and I'm going to create a new Python 3 notebook. We're going to use another library, import pandas as PD. Again, you have to install this. And I'm also doing from pathlib import path, I believe so I did. I'm just going to compare, I'm just going to copy that real quick. Come on, play nicely. Okay, and then you hit Control Enter and it'll evaluate it for you. So what I'm just doing is I'm just bringing some things into scope. Next thing we're going to do is we're actually going to load our data. And I'm just using a notebook that I prepared in advance. So I already know that my data is one directory up, which is why I divided my path by ... and then I divided by data, and then I divided by the file name. And then I simply asserted that the file exists. That's just a sanity check. Then we can do df equals pandas.read. It's read CSV or is it load CSV? Oops, just double checking here. Yeah. Okay. So what we've done here is we've asked pandas to load the library for us. And we've also said that we want the first column to be the index, simply because I happen to know that's what we need to do. If we have a look at this now, this looks a bit more readable, doesn't it? Right? What we have here is we have tabular data. We have different internet service providers, and we have a date column. Or that's the row at this point, isn't it? It's gonna be the column. All right. So if we were to try to plot this data right now, actually, I'm just gonna do this is just some cleanup steps. I have a cleanup step that I do here. This also demonstrates something you can do with the data frame. Oops. Say I want to rename all of these because there were trailing white space that the thing didn't handle on its own. Well, I can apply an operation to do something on that. For each key, I simply stripped the white space from it. All right, that makes the data slightly easier to work with. The next thing that we're going to want to do is if we say we want to plot this right now, it's probably going to generate a whole bunch of noise. I don't know about you, but this graph is meaningless to me. Don't worry, we'll get to the point where it is meaningful. When you're working with data, sometimes the format you're provided with is not necessarily 3 lines and you have a graph. Sometimes you have to do manipulations. In this case, what would really help is if we flip this axis with that axis. Numpy happens to have something that we can do that with. It's called df.t. It'll transpose the data. Now we have something that looks more like time series, which is what we actually have. And if we were to plot this right now, we actually get some meaningful information out of this. So for reference, this particular data set was provided by Netflix. This is data back, I believe, between 2010 and 2015, sorry, 12 through 14. And this shows the metric of, for each ISP, you have the mean download speed for all the customers that Netflix was serving at that point in time. Between November of 2012 and to about February of 2014, the download speed for several of these ISPs was falling. This is showing a trend. And then between February and July of 14, they all suddenly spiked right back up again. There's actually a reason for that. And in the slides, I actually provide links that way you can read some of the news articles that is relevant to this. Let's see. Should have. Where did I put that? Did I put that over here?
Just had it.
Oh, I did?
Right there.
There we go. No, actually.
Scroll up. Right there, right there.
Yep. Okay. So that's the actual citation. I actually provide some other links to news articles, but I can't seem to find that slide at the moment. It may not have made it into the earliest version. Anyways, so that's where I got the citation from. I actually had difficulty locating this. I originally gathered this data back in 2018 when I was doing some stuff for Saddleback. I was doing a class at the time. It was an English class. But it's not really important. Anyways, so this is just to demonstrate in a very basic capacity what you can do with data science. Is you can take some data and you can get some meaningful information out of this. For instance, that might spark the question, well, what the heck happened here? That is such a giant leap, right? Well, what actually happened there is Netflix ended up paying a ransom to the ISPs in order to get that speed. If you look it up, in fact, I don't have time, otherwise I'd show you the articles, but that's a basic demonstration of what you can do with data science. There's other things you can also do with the data frame. So if you go back to the data frame, right? And I'm going to just do df dot. So I believe I can do .loc Comcast, and then I can just get the time series data for Comcast itself. LOC basically allows you to get at the keys on the row, because by default, if you do the subscript, you will say I will get everything. Say no 12. If that works, it does, and now we'll give you the value for each individual provider. Sometimes you only want to look at one data point out of a larger data file. And other times, you might want to do something slightly different. Let's see here. So if I were to do all of those will be false, but I will demonstrate what this does in a moment here. Say 0.5, and most of that will be true, yeah? All right, so if we look at our data, and I'm just going to say everything that is below 1.5, and we will get something. What we're doing here is we're actually using the relational operators to do a comparison against the entire data set. So I'm saying every value that is less than 1.5, which basically only really occurs for AT&T's DSL line, because DSL is slow. I apologize if your home internet is on that. What we further do is we can actually stick that in the middle of here. I would actually have to filter nans, but this is more clear with the series. I'll show that in a moment. What we can see here is, well, we've gotten rid of all of the data except for the data that matches that filter. This is something else that you can do with both a pandas data frame as well as a Numpy series, which I will now show you. All right. So with Numpy actually has a function to two different functions you can use to generate just an array of data. The one I will use here is going to be numpy.arange. Data equals np.arrange. I believe that's what it is. Is that what it was? Yes, excellent. By the way, if you have a symbol and you just put a question mark, and it'll bring up the doc string for you. That's one of the things you can do with a notebook. Anyway, so if I do that and then look at data, we now have an array of data. Say I want to have just the data, subset of the data that's even. Data mod 2 is equal to 0. And now we only have a subset of the data that's even. We can invert that and say that's not equal to 0, and therefore anything that has to be odd, so on and so forth. So these are some of the things that are very easy to do using the scientific Python libraries as it relates to numerical analysis and data science that are actually somewhat much more difficult to do with pure Python libraries. The last thing that I'll talk about today is some of the common pitfalls when you're using the Jupyter Notebook. Because this thing while being incredibly powerful when using data science. For instance, it will render your data frames, or will help you do your plots. The one thing that can catch you is the fact that I can go back to the cell and I can completely edit it and make it do something different. And now I've broken the order of the data frame. When you're writing a Python script, you're editing your source and you're running it, you'll always be in the correct state. However, if I were to do something like this and say none, you'll see that none of the rest of the cells have been reevaluated. And if I were to rerun this notebook right now, and just press this big red button, my notebook suddenly throws a big fat error. So this is demonstrating the fact that a Jupyter notebook is stateful. And if you're not aware that the state exists, you'll shoot yourself in the foot when no one can reproduce your notebook, because you've been exploring the data and you've been rewriting these cells over and over again. You finally got the result you want, but because you haven't restarted the notebook in forever, you might not be able to easily come back to that data. So the easiest way to avoid this particular issue is whenever you've modified a cell, like if I were to modify the cell in the middle here, and there was code after this, is to press this restart button. Restart and run all cells. If you do this every time you've modified your code, your notebook will always be consistent, which means anyone who runs your notebook with the same data should be able to reproduce your work. Questions? All right. So I think the last, how much time do I have left?
0.
0, in which case that's all I have time for.
No questions for Josh? All right, thank you very much. Nice.
You got a question?
Yeah.
What was the link for the PKF?
Oh, yeah, sure. Why am I in caps lock? GitHub, the unknown one. ECI Bootcamp 2021, and let's go ahead and put this on the board as well. This is the repository which contains all the sample code as well as data if you want to try to reproduce anything that I've demonstrated here today. And from there, you'll also find a link to the rendered version online. All right.
Next talk of the day is gonna be on SQL. Richala is back to talk to us.